Hello and welcome. Today we will be diving into the concept of handling data consistency in distributed systems, part of our advanced topics in system design. In this presentation, I will be taking you through a series on cutting edge system design principles. Let's get started. Here's what we will cover in today's presentation. First, we will introduce data consistency and discuss the challenges involved. Then we will explore the Cape theorem and various consistency models. We will also look at eventual consistency and its implementations. Later we will examine CQRS, event sourcing, and how consistency is balanced with latency. Finally, we will conclude with some real-world case studies and protocols that help maintain consistency in distributed systems. Data consistency refers to ensuring that data in a distributed system remains accurate, reliable, and synchronized across all nodes. Achieving consistency is crucial but challenging due to issues like data replication, network partitioning, and concurrent updates. In large-scale systems, consistency becomes even more critical for maintaining reliable operations. One of the foundational principles in distributed systems is the Cape theorem, which states that a system can only guarantee two out of three properties: consistency, availability, and partition tolerance. If a network partition occurs, the system must either maintain consistency or availability, but not both. This trade-off plays a major role in system design and needs to be carefully considered. To handle data consistency, we employ different consistency models. Strong consistency ensures that every read reflects the most recent write. Eventual consistency allows for temporary inconsistencies with the promise that data will converge eventually. Casual consistency maintains the relationship between updates, while read your writes consistency guarantees that a client always reads its own updates. Eventual consistency is a model where data replicas across a system will eventually synchronize, but for a period of time. There may be inconsistencies. This model favors availability and partition tolerance, allowing systems to continue functioning even if some replicas are out of sync. Examples of systems using eventual consistency include Amazon DynamoDB and Cassandra. CQRS, or Command Query Responsibility Segregation, splits the responsibilities for reading and writing data. This approach enhances performance and scalability. Event sourcing takes this further by storing all changes to data as immutable events, providing better scalability and ability to audit and track state changes over time. Both of these concepts work well in systems that need to scale while maintaining consistency. When designing distributed systems, there is often a trade-off between consistency and latency. Lower latency means transfer response times, but it might come at the cost of eventual consistency. On the other hand, prioritizing consistency can result in slower responses. Depending on the use case, systems must decide how to balance these factors. Achieving consistency in distributed systems is not without its challenge. Network partitions can cause nodes to lose connectivity, leading to data inconsistencies. Replication lag refers to the delay between updating a primary node and the time it takes for that to change to propagate to replicas. Additionally, concurrent updates can lead to race conditions where Simultaneous data updates may conflict with each other. In databases, relational databases typically guarantee strong consistency using the ACID properties, while NoSQL databases often prioritize availability and partition tolerance, allowing for eventual consistency. Hybrid models like Google Spanner combine strong consistency with high availability, providing the best of two worlds for certain use cases. To maintain consistency, various consistency protocols are employed. Quorum-based replication ensures that a majority of nodes acknowledge a transaction before it's considered successful. Two-phase commit or 2PC ensures that all nodes in a transaction agree before committing changes. Consensus algorithms like Paxos and Raft are used to ensure that a group of nodes reaches agreement on the order of operations in distributed systems. Let's look at a case study on Amazon DynamoDB, which uses eventual consistency to ensure low latency reads and writes. DynamoDB prioritizes availability, making it a great choice for highly distributed systems where near instant access to data is required, but the latest data is not always necessary. Social media platforms like Facebook and Twitter are perfect examples of systems that use eventual consistency. When you update your status or post, it might take a while for that update to appear on every device or in every feed. The system focuses on quick updates and fast responses even if the data isn't immediately consistent across all replicas. In summary, handling data consistency in distributed systems requires balancing between consistency, availability, and partition tolerance, as described by the Cape theorem. Choosing the right consistency model using protocols like Paxos or Raft and understanding the trade-offs between latency and consistency are key to building efficient and reliable systems. Real-world examples like DynamoDB and social media illustrate the practical application of these concepts. Thank you for your attention. I would now like to open the floor to any questions or comments. Feel free to ask anything or share your thoughts on how these principles would be applied in your own systems.